This is Components of Quantitative Analysis Series, an introduction for clinical investigators. This is part 3, Introduction to Model Evaluation. So just to recap where we've come thus far, when we talk about models, we're saying that we're taking some output that's predicted from inputs, output being y, inputs x, using some function f. Again, this could be any function, mathematical. It can be qualitative, but again, for our purposes, we're thinking about quantitative models. The application, in general, we tend to focus on prediction versus inference. Again, models can and usually produce both, but the focus is typically one or the other, and certain models tend to be better for one or the other. The type of model, as we talked about in the last session, tends to be based on the parameterization of x and y, which is based on how the information is represented or measured as data. Again, the whole point of this exercise is to try to model information that we deal with in the real world as bits of zeros and ones or numbers that we measure as data. And so when we turn to model evaluation, what we really want to know is how good is the model. Ultimately, the question is it useful, which only, can be determined through prospective application and trial and error and seeing if it actually, helps guide decisions or whatever we're using it for. But of course, I think before that we get to that point, we like to know if we can trust the model, and that's where a set of standard categories can be used. It really applied to all models. That's what we'll sort of talk about in the rest of these sessions for this part. So I tend to kind of group the categories of model evaluation under 4 pillars. These are accuracy, calibration, interpretability, and uncertainty. Again, this is my own sort of categorization, and as we go through these sessions, you'll see that there's a lot of overlap, and certainly in some instances we'll actually kind of discuss them under different parts. But at the end of the day, I think most models we tend to kind of think of as along these groups. And so accuracy, we're basically asking the question: does the predicted value of y match the actual value? Pretty standard question. Again, this is not accuracy necessarily. There's a metric of accuracy that's a specific statistical measure, but here we're sort of talking about in the broad sense. Does it actually predict what we think it should? Calibration is the question of does it work across all groups? I'm just sort of shown here. This is a calibration curve that we'll go into a little bit more for certain types of models. Again, this can be applied at both the model level, but also broadly, as in, can we trust this model would work in different populations? And we'll talk more about that. Interpretability, I kind of group as a sort of forward versus backward. The forward is sometimes called mechanistic. Can I walk through the model to get to the predictions? Meaning, can I trace out the steps from where I get from the inputs of X to the output Y? This also goes the other direction, backwards, or what's sometimes called post hoc interpretability, which is, can I understand why the model predicted what it did? So I think of the forward as how, the backward as why, based, which X's were most important for predicting why. And then finally, is uncertainty, which is kind of this broad category that I will say we'll kind of get into a little bit of the types of uncertainty, which can, in some cases, people have tried to measure this quantitatively. Other instances, it's sort of a conceptual idea. But I tend to kind of group these into two subcategories. Model uncertainty, meaning for which inputs is the model more or less certain, and then the prediction uncertainty, which is when it's applied, can we say for an individual whether it's more or less certain? And we'll talk more about how we kind of can parameterize those things. So just thinking about these pillars more closely, again, accuracy, again, how closely does the predicted y match the actual y? And as we'll see, this is really strongly determined by how we parameterize y. Whatever we're representing y, there's a way to measure whether it's accurate or not. And that's actually the most important determinant for whether we, quantitatively say that a model is accurate. In terms of calibration, again, this is sort of saying how well does the model predict y, across different groups. It's in a way it's kind of like accuracy because it's looking at accuracy, but it's breaking it down into different individuals or groups within both the population it was fit in as well as external populations. And critical to this is this idea of bias or confounding, as well as whether the model actually fits. And again, we'll talk in a little bit about how model fit versus bias confounding is sort of a thought of at different levels. But again, fit being kind of more of an outliers thing, bias confounding more across populations. Interpretability, again, as I mentioned, the how is kind of the walkthrough mechanistic. Are we able to walk through the model to see how the predictions are made? Certain models, for example, risk scores are, easily interpretable in terms of how you add up the numbers based on each of the inputs and you get, the predicted output versus the why, which is kind of working backwards. As again, discussed this as kind of post hoc interpretability. Do we know which X's were the reason or the cause for the prediction? And again, moving backwards into our framework of prediction versus inference, we can kind of see that this is really the critical part of an causal inference or an inferential model is which X's were the cause of the prediction. And so again, you can see how for certain applications, this is an absolutely critical component, whereas for others, such as a kind of black box prediction, we sometimes have to just throw our hands in the air and say if the prediction is accurate, it's accurate. And then finally, the uncertainty. Again, I think of this as sort of the uncertainty at the level of the model. And this is important because if the model is uncertain, we can actually improve it by making better models, sometimes through collecting more data or maybe reparameterizing the model. Whereas the actual prediction has its own sort of level of uncertainty, which is if I produce a predicted probability, do I know how confident I am in that? And does the model produce that, level of uncertainty, which is kind of what we're looking for in an evaluation. What's absolutely critical in this, and one of the things that I think we've sort of uncovered as we've thought about how to, formalize model evaluation, is this idea of levels, because it turns out that, who's doing the evaluation determines a lot about what we're going to look at in a model. In terms of like the context, or we call them, the levels of evaluation. And just as an example, like let's say I have a model to predict incident disease. If I'm a statistician or an analyst, I want to know, what's the data distribution? Does the data, the distribution of the data fit the target distribution, which is often what we're trying to, to use to create a model? What observations have the greatest leverage or influence? What are the confidence intervals around the prediction? Again, these are sort of quantitative, technical components of a model that an analyst would be looking very closely at. Um, in contrast, sort of your clinician end user, is going to look at this more holistically. Does the prediction change the probability of disease? The model numbers may add up, but does that actually change, what I'm going to do about in terms of management? Does the population of derivation match the population of application? This is absolutely critical, this idea of population bias, or, what model can be developed in one population. And if you know clinically that the population you're going to apply it to is completely different, then that's really important and something that really only the clinician end user can kind of, understand those differences. Do the most important predictors match what is known about biology? Again, you know, in theory, the clinicians, we have, a wealth of biological, understanding of physiology and systems, and, is it plausible that the prediction could even, make sense based on what we know biologically, and then ultimately, can the predictions be trusted? Again, sure, we have confidence intervals, but at the end of the day, when I go to, apply a model in the clinic, what do I care about in terms of whether I can trust that? Um, and again, I think of sort of bookending these. On the one end, you've got the policymakers. Again, they're looking at, even more holistically. What are the costs of applying the model? What's the sort of technical demands? Is it feasible to apply a model within sort of a healthcare system, or across populations? And again, they're going to be especially concerned about population-wide benefits, or the population-wide characteristics of the model. And then, of course, on the flip side is the patient, right? I mean, at the end of the day, they want to know, does this, process impact my health, or can I make an informed decision based on this? Again, these are important considerations, depending on your level. And again, each level is going to potentially look at each of the four pillars in their own sort of lens, and I think for simplicity, for the rest of these sessions, we're really just going to focus on these two, mostly because, the two are related. So I don't want to present them as if they're completely different ways of looking at it. They're all looking at the same thing, but it's through a different lens. And actually, the information from one is absolutely needed to inform, what's used in the other. And so I think this is really going to be the focus, is sort of, framing these as sort of how would a statistician or analyst, what are they looking at when they evaluate a model versus a clinician or sort of end user, like what are they looking at, and how does the two, angles of looking at a model, how do they interact to actually come up with an overall evaluation of the model? Um, And so just sort of thinking about sort of levels for pillars, again, clinicians, we bring, we have the substance matter expertise. We understand biological relevance. We understand what's clinically, applicable. We, should understand kind of ideas of confounding or bias, at kind of a high level, based on what we know about patients and how, disease is distributed. And again, we bring real world experience, what's feasible, what's not, absolutely important in evaluating models. Again, clinicians are generally, we're going to be less interested in the how the data was transformed within the model, what are the mathematical operations. Again, some clinicians are more or less, interested in that, but, and it is important, which is the whole point of these sessions. But again, I think the nuts and bolts of, of variables and, numbers is going to be less important than what the actual meaning. Again, clinicians thinking in terms of information as opposed to the actual data. On the flip side, what we're the conclusions we're making about the information come from data that's being manipulated by analysts. And so, that technical knowledge is going to be absolutely important in evaluating models. A technician or an analyst is going to understand all the assumptions that are requisite to each modeling approach. Based on the parameterization, there's certain assumptions that are, critical to consider. They're going to be aware of all the quantitative tools that we can use to inspect the models. In a lot of cases, they've developed those tools, or know how to kind of modify existing tools in a way that might be applied to a model. And importantly, know, if an alternative model that might be used. And so, again, they're going to have less knowledge about the actual information that's involved in the model, whether the information is actually connected to data in a meaningful way. But really, important as well to understand if, once we start using the numbers, does it make sense what we're doing? Is that, consistent with the mathematical properties? And so overall, I think it's important to just realize that this is a collaborative exercise, and that, the goal of these sessions is going to be kind of to bring the clinicians closer to the quantitative side, to understand some of the methods, to understand kind of, what an analyst is thinking when they work through the data. But again, it's not going to replace an analyst, and certainly we're not going to get into all the details of how you code models, how you the different packages and things that can be used. Certainly you can explore these, and I would encourage any clinician to do that. But ultimately, we're going to try to come up with a way that brings it all together, so that we can understand if a given model is presented to me, how would I evaluate that critically? And that'll be the goal of the rest of the exercises.